now that we've established that energy can't be created or destroyed, it has to go from one place to another place, we're going to focus more on that amount of energy. And we are going to call that enthalpy. So any energy associated with heat, okay, this change, not phase change, sorry, for a chemical reaction is called enthalpy. Okay, so we said heat was represented as a Q, and enthalpy is heat flow. These are all related. They're kind of synonymous. Q, heat, enthalpy. And we're going to talk about how to measure that and how the quantitative amount plays in. So enthalpy is called a state function, and that means that this property, enthalpy, depends on the present state. Okay, so like what state is it in now? It means it doesn't matter what the path was to get there. So I like to use this as kind of an example of like what a state function is. There's path A, which is 12 miles to get from the bottom to the top of this mountain. There's path B over here, which is only 5 miles to get from the bottom to the top to the bottom, either way. But one is longer than the other, but you still have the same starting and ending point. So enthalpy is something that's a function that's like that. Doesn't matter how I got there, what path I took. It just matters the difference between the top and the bottom. No matter what, this is a difference of 10,000 feet. So enthalpy is something that doesn't matter how you got from point A to point B. It's just the difference between the beginning and the end. Okay, I'm going to get more into that in a little bit and why that kind of matters. So enthalpy, again, is a state function. Enthalpy is with the letter H. Now, when you take 162, we're going to have words that are similar to enthalpy, like entropy. The way that I remember that enthalpy is H is because there actually is an H in enthalpy. And this is heat. Heat starts with H. So heat can be represented by Q or H. Heat, enthalpy, Q, H, all kind of synonymous. Okay, they all go together. They're all kind of the same thing. They just have a little bit different definitions, but heat, energy, enthalpy, all of that same thing for our purposes. Okay, so enthalpy is the measurement of heat flow for a reaction. So a chemical reaction has a specific value of quantitative heat flow into or out of the reaction, depending on if it's endothermic or exothermic. Okay. This value is an extensive property. That means it depends on the amount, which makes sense, right? If I burn 1 gallon of fuel, it produces a certain amount of heat or energy. Whereas if I burn 2 gallons of fuel, I'm going to get double the amount of heat or energy. Okay, that's what an extensive property is. And we talked about those in like module 1, I think. So the equation to find the amount of enthalpy for a system is based on the internal energy and the work that it does, which has to do with pressure and volume change. If you're talking about a gas, this equation specifically, we are not going to be using because we are not talking about gases in this specific unit. We'll talk about gases in their own unit. So again, we're not focusing on the whole expansion and compression of gases. We are focusing on heat transfer, energy changes from hot to cold. That's what thermochemistry is all about. Okay. So here we're doing thermochemical equation. So what does the equation look like? What does enthalpy look like? And we're going to start with this equation here. Now, this is one I use a lot. It is nitrogen reacts with hydrogen to make ammonia. You don't have to know that that's called ammonia, but it is a very common molecule. I would know that it is called ammonia, NH3. Okay, so for this balanced chemical reaction, this represents 1 mole of nitrogen reacting with 3 moles of hydrogen to make 2 moles of ammonia. The amount of enthalpy or energy associated with this reaction is negative 92 kilojoules. Now, remember when I told you that negative Q or negative H, they're the same thing, means it is exothermic. That means that heat is going out of the system. If it is exothermic, it is negative, is going out of the system. So this means for this balanced reaction, 92 kilojoules of energy will be exiting the system. Okay, negative means it gives heat off, exothermic. Okay, so we actually represent that by, this is called a reaction coordinate diagram or a reaction diagram or whatever you want to call it. It's usually time, or it might say reaction coordinate down here, and then potential energy over here. And the way these are set up is that this is the energy of the reactants. So right, I said there's energy associated with the bonds and things in a molecule. That's why the potential energy starts here. And this is the energy of the products. It's down here. So I said that delta H is a state function. The path to get there, this path here, doesn't actually matter. Could be a high, what's called activated complex or activation energy, could be low. Delta H is the difference between reactants and products, only from the reactants to the products. That's the difference in that. The delta means difference in, that is like beginning and end, is right here, the difference between the reactants and the products. So if I have this reaction coordinate diagram, to find delta H, it is the difference between your reactants and your products. That's it. The energy difference, that potential energy difference between reactants and products. Okay. If the energy went from a higher energy to a lower energy where the products are, it was negative. It was exothermic. Okay, down here, if it's opposite, if you started lower and ended higher, I had to have put energy in. So that one is positive. That is endothermic. So looking at this reaction diagram, you can see right here, if it goes down, it's negative, it's exothermic. If it goes up, it's positive, it's endothermic. So a question you might be asking is, well, what is this big hump here? All equations have some type of activation energy. Some have a very low activation energy. Some have a higher activation energy. That's like to get the reaction going. So kind of like if you're going to burn something, you're going to combust something, that spark that you need is the activation energy, and then the reaction will go. And the top peak is called the activated complex. That's a really high energy thing that's not very stable. This is more in the kinetics of a reaction. This is not something we're going to focus on in Chem 162. We just want to focus on the difference between reactants and products energy. Okay, so down here I said this one would be an endothermic reaction. So if I've got mercury oxide or mercury 2 oxide, and I want to break it up, this is an endothermic reaction. It requires energy. I have to put energy into it. It requires 181.6 kilojoules to turn 2 moles of this into 2 moles of this and 1 mole of this. Okay, so looking at this reaction diagram, my reactants start here. My products go here. The energy must be put in. It is positive. It increases in energy from reactants to products. So this is endothermic. Okay, so let's look at example 1. It says, for the following thermochemical equation, determine what happens to the delta H for each case. Now, remember, I said delta H is an external property, which means that if you double the amount of stuff, you're going to double the amount of heat. So it depends on how much you have. So this amount of energy is for this balanced chemical equation. So 1 mole of this and 3 moles of this, making 2 moles of this, gives off negative, means it gives off 92 kilojoules of energy. So what is the delta H for this reaction? This is 2 NH3s, sorry, that was a typo, NH3s, make an N2 and a 3H2. Well, how is this related to this equation? You might be able to see this is the reverse equation. So if the first reaction gives off 92 kilojoules of energy, well, if this is the reverse reaction, that means that the delta H for this reaction is positive 92 kilojoules. So to make it go backward, you would have to put in 92 kilojoules of energy. Okay, so 1 is negative and 1 is positive. Now, what happens when you start changing the numbers? What if I had 2 moles of this and 6 moles of this to make 4 moles of this? Well, this is just doubling the reaction. So you just double the amount of energy. So for this one, which is doubled, delta H equals 2 times negative 92 kilojoules. So that is negative 184 kilojoules. Now, that's going to be important later when we do Hess's law as well. But now I want to know, I'm going to do these reactions in the lab. How much energy am I going to produce if I use 16 volts of NH3 or 6.8 grams of NH3? Well, anytime you have a reaction like this, right? This is a reaction, which means it's stoichiometry. I can use a ratio to figure out how much energy is going to be produced. So anytime you have a reaction, right, it's stoichiometry. Now, instead of a mole ratio, though, you're going to use moles and energy. So think about it, the same 3 steps that we usually use, convert to moles, and then use your ratio. But at the end, you're actually not going to have to convert to anything else because you're going to have your answer. So it says, what is the delta H if 16 moles of NH3 are produced? So I'm going to start with the number I give you in the problem, 16 moles of NH3 over 1. Well, I don't have to convert to moles because I'm already in moles. So now I need my mole ratio. Well, it's wanted over given. Well, I was given moles of NH3. So I'm going to look at my balanced equation and it's got a 2. So this would be 2 moles of NH3. And what do I want? Well, I want delta H. And for 2 moles of NH3, it was negative 92 kilojoules. So you would write negative 92 kilojoules. Okay, so instead of a mole ratio, you're going to use one of them is going to be moles and one of them is going to be the energy because this negative 92 goes with 2 moles. Okay, and then that's what I want to know. I want to know delta H or energy, so I don't have to convert to anything after that. I would just stop there and do the math. And it would be negative 736 kilojoules. Okay, so that was if I had 16 moles. Now, of course, in the lab, we don't measure in moles, we measure in grams. So part D says, what is the delta H or the enthalpy if 6.80 grams of NH3 is produced? So now I'm going to start with 6.80 grams of NH3 over 1 times, now I got to use my full steps for stoichiometry, convert to moles because I'm not in moles yet. So there are 17 grams of NH3 in 1 mole of NH3. Then I use my mole ratio, wanted over given. So I was given NH3. Again, from the balanced reaction was 2. So it would be 2 moles of NH3. What do I want? I want energy. I want delta H from the balanced equation. That was negative 92. And solve there. Those cancel, and I'm left with kilojoules. So this answer is negative 18.4 kilojoules. So really what that is the enthalpy or the heat or the energy associated with using 6.80 grams of ammonia or making 6.80 grams of ammonia.